All right, so the next step in simplifying circuits is called universal gates. We're going to be looking at a NAND gate and a NOR gate. The NAND gate is basically an AND gate with an inverter after it. So basically you're running your two inputs into an AND gate, and then after it goes through the AND gate, it comes out as an inverter, or with an inverter at the end. So let me see if I can kind of draw you what I'm talking about. So you'll have your AND gate, and then it goes into an inverter, kind of like that. All right. So this is what a NAND gate will look like, and we'll talk about what the NOR gate looks like in a minute. In fact, I think it's probably going to show us. So let's just get started so you know what we're doing, or not. Okay. So basically, it's going to show you how to do NAND and what the function is of a NAND. And then you'll understand, you guys have already seen this once before when you did your labs with NANDs and NORs, and we even talked about an exclusive OR. You guys did those and you went and put them in your labs, and then so you should have all the truth tables for all of these already done. But basically, we're going to be looking at equivalent circuits and how you can simplify using NANDs only. So this is your NAND. Has an inverter at the end, so it looks like an AND gate, but then it has this little inverter. Which basically means that you're going through an AND gate and then you're inverting it after. So this is the typical logic expression for it. You put a line over both, okay? But just so that you're aware, X, Y inverted does not equal X naught, Y naught. Those are not the same thing, okay? When you have one line that goes over both variables, that means it went through the AND gate first and then gets inverted. And when you have the line over each individual one, that means that they're getting inverted before they go into the AND gate. So this is a NAND gate, just like that. And then this one is basically inverted and inverted, then into an AND gate. Okay, two totally different circuits, two totally different logic expressions. I just want to make sure that you guys are aware of that. So make sure that if you are trying to say X naught times Y naught, those are separate lines above it. Don't make it one line across, because that's XY inverted, or not XY, however you want to look at that. Okay, does that make sense to you? Those are two different things. And again, you already have this in your notes. You already have the truth table. Should be in one of the things that we did in the lab before we got too far into this. So let me do something real fast, because that's going to annoy me. Okay, got to mute that music. Okay, so that's your NAND. Everybody already had that. Should have already had that. Okay, so this is an equivalent to an inverter. When you have one input that is both inputs, so like it's going into both inputs of your NAND, that just inverts it. So this is what you're going to draw in your notebook. Here, let's go ahead and get that too. But basically, that is equivalent to an inverter, which is just this. All right. So in your notebook, just make sure that you're putting in your input is going into both sides of the NAND. One here, and then it comes out, and that basically makes it an inverter. You'll see why this is important in a minute. It kind of seems obsolete as to why you would want to do this, but I'm going to show you how you can use this to simplify your circuits and make them even smaller. Okay? But basically, that's your equivalent. So we're going to do 6 of these different equivalents so that you can see what each one does. We'll do 3 NANDs and then 3 NORs, and you'll see how this works out to make it easier. All right? So this one's first. This is your inverter. Everybody get it? Okay. So moving on, this is your AND gate. So basically, you have your 2 inputs going into a NAND gate, then you have an inverter at the end of it. So this is basically taking an AND gate, going into an inverter, and then going into an inverter again, which basically eliminates the inverter, or the NAND part, and makes it into an AND gate. So let's see if I can kind of explain that. Basically, this shape here is an AND gate going into an inverter, and then you just took it into an inverter again. When you have an inverter going into an inverter, what happens? If I have a 0 and it goes into an inverter, it changes it to a 1. If I go back into an inverter, what happens? It goes back into a 0, which means we didn't do anything. So they cancel each other out. And you're left with just an AND gate. And that's basically what you're doing. Okay? And again, it seems like you're doing extra work, but you're really not. But the logic expression down here, it kind of explains what's happening. You're doing x times y inverted, and then you're inverting it again. That's why there's 2 lines over it. So anytime you have 2 lines over it, those 2 lines cancel each other out. And then you're left with just the x times y. All right? Don't worry. It's all going to make sense in just a minute. Okay. So does everybody have this one drawn? You have a NAND. You have 2 inputs going into a NAND gate that goes into an inverter, and that makes an AND gate without the inverter, right? Okay. So let's see. Well, let's go to the next one. Okay. The last one. This is an OR gate. Basically, you have this right here, which is an inverter, and this right here, which is an inverter, going into a NAND gate. Just like what I was drawing earlier, where they're getting inverted before they go into the NAND gate. All right? This is the equivalent of an OR. So when you do it this way, this becomes an OR gate. So this is the proof right here. It kind of explains it to you. But basically, as long as you understand that this is what you're drawing out, you'll see how all this ties together and how it's going to simplify your circuits rather than make them more difficult. It looks like it's going to be more difficult than doing an OR gate, but it's not. You'll see. Okay, does everybody get that? So basically you have your X naught here and your Y naught here getting inverted after they go through the AND gate. Okay, then we didn't really go through this, but if you use De Morgan's theorems, this line here, it's called, the saying is you break the line, change the sign. So if we break this line here and change this sign here, that's a multiplication, to a plus sign, you break that line, then you get double inverted lines here and here, which cancel each other out, and you're left with just x plus y. This was part of the Boolean and De Morgan's theorem stuff that I said was optional for y'all. So you might, if you were wanting to know how this all came about, that's all explained inside those De Morgan's theorems. But it's so that if you were trying to make an OR gate and you only had AND gates, you'd be able to do it. Does that make sense? You'll see. Okay. Does everybody have all 3 of those written down? You got your inverter, your AND, and your OR. All equivalents in NANDs, right? These are called NAND equivalents. So, ready? All good? All right, let me show you how we're going to use them. Okay. So they're just kind of showing you, of course, obviously my image is in the way of the inverter part, but that's okay. But basically you have this one here that is your AND gate. You have this one here that's your OR gate, and then under this one that you can't see because of my image that I thought I'd made small enough is the inverter. Okay? All right, so these are the steps on how you're going to do NAND only simplification. Basically, you're going to take your circuit that you've already made, that you've already figured out, your AOI circuit, meaning you're using ANDs, ORs, and inverters. You're going to replace all the ANDs with NAND equivalents, all the ORs with NAND equivalents, and all the inverters with NAND equivalents, and then simplify. Seems like a lot of work, but the more work you do on paper, the less work you do in wiring. So that's kind of the idea. Come on. There we go. All right, so this is the circuit that we're going to be talking about. Of course, we can't see the logic expression. Cool. And I bet I can't move that, right? Nope. All right, whatever. Okay, so I have no way of even knowing what that is. Yeah. Oh, well, we'll figure it out. Actually, you can figure out what it is by looking at the circuit, right? So we should be able to see that you have C naught here. That's a good example. C naught and B. So this coming out is B, C naught. And this one is C, and this one is A. So this is AC. So our logic expression is Z equals BC naught plus AC. That's what it says under here. All right. So now what you're going to do is you're going to take each gate and replace it. So this one you're going to do as an equivalent, a NAND equivalent. You're going to do this one as the NAND equivalent for AND. This is the NAND equivalent for AND. And then this one will be the AND equivalent for an OR. Okay? So you'll see on this next page what they're doing. So that's what we're doing. We're swapping every gate for the NAND equivalents of that gate. So this one becomes an inverter with NANDs. This one becomes an AND gate, which is down here. This one becomes an AND gate, which is down here. And then this one is your OR gate, which becomes this. Okay? So it's a lot of prep work, and it seems like you're doing a whole lot more than what you should be doing. But this is what you'll end up with. You swapped everything in, and now we have a bigger circuit, right? Seems like we've just made ourselves do more work. However, we're not done. So what you're looking for, in order to simplify this, is anytime you have an inverter or a NAND going into, or an inverter going into an inverter. Anytime you have an inverter going into an inverter, they're going to cancel out. So as we're looking through this, what we're looking for is anytime you have an inverter going into an inverter. So these two, see if I can get that to work. These two is an inverter going into an inverter, right? So we can cancel those. Okay, go ahead. This one and this one cancel out. Do you see that? Everybody good? Okay, so then you redraw this without those. Maybe like this. And now our circuit has gotten smaller. We have the same number of gates that we had before, right? But what about this is different? It's all the same type, right? So how many chips come on, or how many gates are on a chip? How many gates are on a NAND chip? If you don't know, it's okay. There's 4. How many gates do we have up there? 4. How many chips do we need? 1 chip. So we can wire this 1 chip up rather than having to wire 1 AND, 1 OR, and 1 inverter. So we've alleviated all of that and made ourselves only have to deal with 1 chip. Does that make sense? A whole lot easier than having to wire up 3 different chips. And if you're doing circuits like this, you can buy in bulk NAND chips and not have to buy ORs and inverters and gates. You can just buy the NAND chips and create your circuits this way and save yourself a lot of money and time. Does that make sense? So that's what we're looking at. It's an easier way. Comes out the same, and you can see right here it kind of breaks it down. You're buying 3 different chips here versus only buying 1 chip here, and you're getting the same circuit. Do you see that? So NAND equivalents, that's basically what we're doing. We're going to see, and we're going to test. And truthfully, you're going to go through and see if it's easier. You test it to see if your NAND equivalents are better, if your NAND equivalent circuit is better than the AOY circuit that you already have. If it's not, then you go back to your AOY and you do your AOY because it's easier. But if it's easier to do a NAND equivalent, then that's what you're going to end up doing. So now, let me show you the OR equivalents, or the NOR equivalents, I should say. Very much the same thing, okay? There's 3 more we're going to look at, so I'm going to pull them up. This is your NOR gate. It's an OR with an inverter at the end. So here's your OR, and then you should have an inverter. And that's basically what you're looking at, okay? This is the logic expression for a NOR gate. And again, you've already got these in your notes. So if you go back to the lab where we did the digital component identification, we did all of these on multisim and then drew them all out. And so some of y'all that did that in multisim and had to draw out each truth table in multisim, you probably remember this pretty well. So that's your NOR gate. I'm going to go through the equivalents now. This is your inverter. Looks exactly the same as a NAND, right? It's the exact same setup as a NAND gate, only you're using a NOR. So you can look at that and say, oh, that's the same exact thing, right? So you have 1 input going into both of the inputs of the NOR, and then coming out is it's inverted. Everybody understand that? Pretty easy. This is number 4 of the 6 that I wanted you guys to write down in your notebook. This is the NOR equivalent of an inverter. Everybody good? Yes. Okay. If not, remember these are on Canvas. You can always go back and get them. All right. This is the OR equivalent, or NOR equivalent of an OR. Okay. If you look at it, it's the exact same thing as the NAND equivalent of an AND, only you're using NOR gates. This is the NOR equivalent of an OR. It's very similar. They're very similar. That's why I'm mixing them. Truthfully, there's 2 labs to this, but I'm combining them both into one because I don't see any point in teaching you once and then teaching you twice the exact same thing with different IC chips. I'm not going to lie, most of the time, ORs don't work out to be prettier, but sometimes they do. So that we test it just to see. Because sometimes you'll get away with only needing like 1 or 2 gates versus needing an entire chip on NANDs. Sometimes it might be better than that. Okay, so does everybody see that? 2 inputs going into a NOR and then it goes into an inverter. And that's basically you end up with 2 inverters, right? And those cancel. And you just have a NOR. Or your OR left. Does that make sense? All right, so moving on. The last one is this one. This is your NOR equivalent of an AND gate. Okay. Again, you have 2 inverters here, 2 inverters, and then your NOR gate. This is your proof over here, by the way. And again, we didn't cover De Morgan's, so you probably won't recognize how to do this, but De Morgan's theorems would have shown you that that's how it would have worked out. So typically I like to go through Boolean and De Morgan's, but we're short on time, so I just need you to get the concepts first. It's going to be fine. All right, is everybody good? Still writing? I don't want to go too fast, but we are about done. Okay? All right, so now we have our 3. Should show them up here again, where you have this is your AND equivalent, or NOR equivalent of an AND, NOR equivalent of an OR, and then what's over here, which is your inverter. Okay? Those are the 3. So you should have 6 total circuit equivalents that we've done, NANDs, 3 NANDs, and 3 NORs. All right? So going back, doing the same thing. We're looking at the same even example. Okay? So we're going to take this one and we're going to make a NOR equivalent. This one, NOR equivalent, NOR equivalent, and NOR equivalent. Okay? Does that make sense? This is the exact same one that we just did with NANDs, but we're going to do it with NORs now. All right. We swap them in, same thing. So this inverter becomes this, and this and become this, and then this OR becomes this. Okay? This is not going to look as pretty as the NAND equivalent. I'm just going to put that out there. All right. You ready? All right, but that's all you're doing. You're taking your circuit and your gates for each one and swapping them with the equivalent. Okay, so there we go. We put in our equivalents. And now we're going to start looking for any time you see an inverter going into an inverter. So here's one inverter, and there's an inverter. So these will cancel. This one does not have an equivalent before it. This one doesn't have one, and neither does this one. So the truth is, that's the only simplification I can see for this one. Just those 2 get canceled. So if you're looking at this NOR equivalent, this did not get nicer, did it? It's still better, though, than doing the AOI, because how many chips do we need? 2. Should be 2. You've got a set of 3 right here. There's your 4th one, and then you've got 3 more gates here. So you're going to end up with 2 chips, okay? Which before we had 1 AND, 1 inverter, and 1 OR gate. So that's still 3 chips. So this is still better than what we had originally. But you can't see back here, but basically there's 7 gates, which means 2 chips. Okay, versus the 3 chips that we had over here. So less chips that you have to buy, but truthfully not a whole lot easier to wire. So which way would you be more likely to use? Between the NOR, the NAND, and the AOI.
No.
The NAND, right? Because that's a whole lot easier. So the next project that you're going to be doing, you're going to be designing circuits, and you're going to get to decide how you want to wire them up. You're going to determine what is the easiest way for you to wire things up based on all the simplification that we have. Does that make sense? That's what we're headed towards. All right, so that